Hi guys, we're going to talk a little bit about electronegativity and its effects on bonding. So what I've shown here, I've tried to kind of condense some important elements from the periodic table. Here I have groups 1 and 2, hydrogen, lithium, sodium, potassium, and go all the way down here. Group 2 elements, beryllium, magnesium, calcium, and in parentheses I have what are called the electronegativity numbers. Now electronegativity, at least this scale, was originally developed by Linus Pauling, very important chemist and social activist, by the way. He's actually the only person to win both a Nobel Prize and a Nobel Peace Prize. So Linus Pauling came up with what was called the Electronegativity Scale, where fluorine, which is the halogen that's in the uppermost right corner of the periodic table, notice it has a value of 4. So fluorine is the most electronegative atom. All of the other atoms are going to have values less than that. And you may recall from your general chemistry, when you're looking at a larger periodic table, that as you go up a column, okay, so as you go up this way, or across a row like this, you have increasing electronegativity, which I'll just abbreviate as En. So looking again at our trends here in the metals, as we come up from the bottom, notice our numbers are starting to go up. And then as we go across this top row, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, you notice that they are getting larger. Now in our organic chemistry class, we're going to be mainly focusing on elements that are going to be in the upper right-hand portion of the periodic table. Occasionally there will be metal salts that we might be discussing, but most of the action is going to be happening actually at this element, carbon. And then there may be other things attached to carbon, nitrogens or oxygens, silicon, sulfur, possibly phosphorus, halogens. We'll be talking about those. But I wanted to present this electronegativity scale in this visual way, just to help remind you that you can always go back to the periodic table and just look at what is that electronegativity trend. So what's the effect then of having a bond between different atoms? So let's say we had a carbon and it was attached to a nitrogen, or a carbon attached to an oxygen, or a carbon attached to a fluorine. So if we were looking at these bonds, and I asked you to sort of rank which bond was the most polar bond, what would we be looking at in this case? Well, when we talk about a polar bond, we're talking about an asymmetric distribution of electrons. And when it comes to electronegativity, the more electronegative the atom is, the more ability it has to pull electrons towards it. So if we look down at this carbon-fluorine bond, this fluorine is essentially acting like a much larger magnet, if you will. It's pulling the electrons away from carbon than would this oxygen, and even more than the nitrogen. So if we were to draw polarity arrows, and you typically draw polarity arrows in the direction that the electrons are being pulled, or towards the negative area, and if we were to sort of make these sort of look like vectors with the direction and size or length of the vector indicating the strength of this polar bond, the carbon-fluorine bond would be the most polar of this series. So this would be the most polar, and this would be the least polar of this particular series. So when it comes to carbon skeletons, things we're going to be talking about in our class, when we start looking at other atoms that are attached, that's going to bring about this phenomenon called polarity, which again is an asymmetric distribution of electrons. And the polarity is always sort of pointing towards the atom that has the higher electronegativity. So carbon is sitting here at 2.5 on the electronegativity scale. Fluorine, 4.0. So there's a difference of 1.5 electronegativity units. So that's considered to be a very polar bond. As one other final thing I'll just mention, when you have elements that are over in this upper right-hand corner, which have very high electronegativities, paired with something that has a very low electronegativity, something like sodium chloride. Okay, so let's write down the value of electronegativity for sodium. It's 0.9. And chlorine, it's 3.0. Okay, so if we just take the difference of those two, we get a value of 2.1 in terms of the delta electronegativity. In general, there's sort of as a general rule of thumb, if this difference in electronegativity is greater than about 1.8 or so, that's considered to be a salt bond, okay, or an ionic bond. Whereas if the difference in electronegativity is less than that 1.7 to 1.8, that's generally considered to be a covalent bond or a completely shared pair of electrons, not as we would see in a salt, where in this case, the chlorine, which normally has 7 electrons, it's going to actually pull an electron away from sodium and have a negative charge associated with it, and the sodium would be positive. That's a fully ionic or salt bond. These types of bonds that have delta electronegativities, again, less than about 1.8 to 1.7, they're considered covalent bonds. So we'll come back to this topic of electronegativity time and time again when we're looking at molecules that have a variety of different elements. It's a really important topic, and we'll make sure we get some practice when we get into our lecture sessions on this. Good luck.